So we're going to continue with our limits. In part 3, we're going to also evaluate some limits, but we're going to specifically work with the functions or the equations themselves. And we're going to pay particular attention to piecewise functions and how we work with those. Okay, now when you're dealing with easy situations of things being continuous, that's kind of the best bet or the easiest way to kind of work with finding the limit with the equations, because if everything's continuous and all the points line up with each other, all you need is that x value. You're going to plug it in and find the y value, and since everything's continuous, your function's going to head towards that point anyway. So for functions that don't really have a domain error at the x value you're kind of investigating, you really don't have to worry about any special patterns or anything. You just have to plug the point in and figure out what happens. It's referred to as direct substitution. So for the very first task, where the limit as x approaches 1 of this quadratic function, since quadratics are continuous on their domain, they really don't have any holes or asymptotes or anything weird that goes on with them, we can just plug in x equals 1 and find the y coordinate for it. And that'll also tell us what the limit's going to be. So we're just going to plug in 1 squared plus 3 times 1 minus 7. And we get a grand total of negative 3. So that's going to be our limit. It's just negative 3. For our next example, x approaches negative 1 of this rational function here. We don't have an issue with negative 1 in the domain because the only domain error we have is negative 6. And since that's not what we're investigating here, we're not taking a look at what happens at negative 6, but rather what happens at negative 1. We don't have to worry about it. We can just plug it in. It's part of the continuous part of this rational function. So we're just going to plug that in. So negative 1 plus 1 all over negative 1 plus 6 ends up being 0 over 5. That is a grand total of 0. That is an actual value. It's a real value. And we're just going to say that the limit is going to be 0. So this is basically talking about the x-intercept of this particular rational function. Lastly, for your piecewise, it's talking about x is equal to 2. So the only piece that's really a part of is this bottom piece here, where x is greater than or equal to 0. That's the piece where we're going to find x equals 2. And that's where we're going to find the pattern around what happens at x equals 2. So we're just going to plug that in. 2 times 2 minus 3. We have 4 minus 3, or just a grand total of 1. So we're going to say that the limit here is just equal to 1. I always recommend going for direct substitution first when you're evaluating a limit problem, more so because sometimes they're fine. You just plug in the x value and you're dealing with a continuous nature and you're fine. So I always suggest to try that out first. So that's what we're going to do for the next couple of problems in task number 2. And these are talking about domain errors specifically at x equals c. So there is something weird that happens at these x values that you're going to see. Okay. First one, the limit as x approaches negative 1 of the following situation. So I'm going to plug in negative 1 first, and we're going to end up with negative 1 plus 1, negative 1 squared plus negative 3 plus 2. And we're going to get a grand total of 0 over 0. This is something that we call indeterminate. Or an indeterminate form. And all this means is that we don't really know what's happening here. This could have a limit. It could not. We're not really sure what's going on here. It's not 0. It's not undefined. It's kind of one of these in limbo. We're not really sure what's going on here. So what we're going to do is use some algebra to help us out. Since this is a rational function, factoring is key with these ones. So we're going to take this expression and we're going to factor it. X plus 1 is in the top. In the bottom, we're going to factor into x plus 2 and x plus 1. So the x plus 1s are going to cancel, and we are left with 1 over x plus 2. So now what we're going to do is investigate what happens with the limit as x approaches negative 1 of 1 over x plus 2. We're going to see what happens. Now, I want to remind you something about rational functions. This function right here and this function right here are exactly the same, except for one key point. x equals -1, the thing that you canceled. That particular spot is a domain error, but otherwise these two functions circled in red are identical to each other. They're completely the same. So if we're talking about what happens at -1 on this first one, it's really going to be exactly the same as what happens at -1 there. Because again, we're talking about a limit. We're talking about what happens as we approach -1. And since both of these graphs are identical, they're both going to approach -1 the same way. What happens exactly at -1 will be different, but they both approach it the same way. And that's what we're really worried about when it comes to limits. That's what we're interested in. What are we approaching? So I'm going to plug -1 into here and figure out what happens. We're going to get a total of 1 in here. So that means that the limit of this expression is going to just be a 1. There's a hole there, but the function is heading towards a y value of 1. Next one. We're approaching -6 of x plus 1 over x plus 6. So now we are talking about something weird that's going on here. So I always try direct substitution first. -6 plus 1 over -6 plus 6. We're going to end up with -5 over 0. This is something that is undefined. So this does mean that there is something weird going on. There is going to be a vertical asymptote happening in this case, because if you look back up here, we can't factor and cancel anything. So there has to be a vertical asymptote that's going on, with this rational function. So how do we figure out what actually is going on with this one? This is when we're going to pull out those one-sided limit ideas, and we're going to talk about what happens as we approach -6 from the left and what happens as we approach -6 from the right, so we can figure out what is happening here. So I'm going to actually draw out a number line just to kind of give us a sense of what's going on. There's your -6. I'm going to try to figure out what's happening here. So as we're approaching from the left, the limit as x approaches -6 from the left of x plus 1 over x plus 6, I'm going to pick a value really, really close to -6 on the left-hand side. Like, what would be something really, really close to -6 over there? We can take a look at maybe x is equal to -6.001. And I'm going to try plugging that in and just seeing what's going on. What's going on with the point that's super, super close to -6? So -6.001 plus a 1, all to being divided by -6.001 plus a 6. In the top part, that's -5.001 being divided by a 0.001, actually a -0.001. Think about what that's going to do. If you take about 5 and you divide it by 0.001, can you use your calculators for a second to help confirm what you think is going on? But you take a number and divide it by something super, super small, meaning you're taking a number and chopping it up into tiny bits, you're going to come up with a lot of different bits, a lot of different groups. So the smaller this denominator is going to get, the larger overall this fraction has a value. So this is actually heading towards an infinity. On the right-hand side of this, on the left-hand side of this, we're heading towards a positive infinity. It's positive because we got a negative over a negative here. And so we're heading upwards towards positive infinity. This number is growing very, very large. So as we're approaching this asymptote, this function's going like that. So now we have to figure out what's happening on the right-hand side. The limit as x approaches -6 from the right-hand side of x plus 1 over x plus 6. And we're going to do the same thing. We're going to pick a value really, really close to -6, but not quite there. So I'm going to say let x be equal to -5.99 for an example. And what would that look like? -5.99 plus 1 all over -5.99 plus 6. So we're looking at a -4.99 all over a 0.01. Oops. Again, a number being divided by something really, really small. And think about if we keep getting closer and closer to -6, this decimal down here gets really, really, really small. When you divide by something super small, it's going to head to be a really large value overall for this fraction. So this is going to end up heading towards -infinity. I know it's -infinity because I have a negative number on top and a positive number on the bottom. So this would be doing something like this. So this is overall what's happening on that rational graph. So as you can see, the limit as x approaches -6 is not going to exist because one side's heading towards positive infinity, the other side's heading towards negative infinity, so it's going to not exist. This is the situation you would want to say the limit does not exist. The one-sided limits, you can include the infinities in there because you can specify left side's going up to positive infinity, right side's going down to negative infinity. You can specify that. You can make that conclusion based on the numbers. But overall, when we talk about the limit, talk about what happens from both sides. Both sides don't agree. They're heading in different directions, so the limit just does not exist. Okay, last task. You have to deal with piecewise functions. We're going to evaluate the limit, and this is where one-sided limits are once again going to come in to help us out with this. We're going to determine the limit as x approaches 0. So the first thing we're going to say is, well, first of all, we're dealing with piecewise, and 0 just happens to be where those pieces all kind of merge together. That's the domain that is kind of stopping the first piece. We got a point somewhere on that domain, and then the other piece is approaching that domain as well. So we have to figure out, where are all these pieces headed towards? Are they all headed in the same direction? So we're going to split this up into the one-sided limits. We have to take a look at the limit as x approaches 0 from the left-hand side of f of x. And we're also going to take a look at the limit as x approaches 0 from the right-hand side of f of x. Now from the left-hand side, this is where the values are less than 0. So that's talking about this top piece here. The limit as x approaches 0 from the left, if we take a look at that function, it's a linear function. So as we get closer to 0, this is also going to be 0. As we're approaching f of x from the right-hand side, we're going to be working with the bottom piece that's down here, and that's also a linear function of 3x. As we're getting closer and closer to 0, that line approaches a value of 0. So since this left-hand limit and the right-hand limit both approach the same number and they're both heading towards a value of 0, that means that the limit does exist. We're going to say that the limit as x approaches 0 of our function will be 0. We're going to do that same analysis for the last piecewise. 4 is going to be our domain value. So we're going to take a look at here where the 4 is in this domain. 4 happens to be one of those domains where we're stopping one of the pieces and moving on to the next one. So we need to investigate what happens, the limit as x approaches 4 from the left, as well as the limit as x approaches 4 from the right. So as we're approaching from the left, things that are less than 4, we're actually looking at this middle piece here. That's the piece where we're going to be less than 4. So as we're heading towards 4, we're going to take a look at this line, 8 minus 2 times a 4. That would be 8 minus 2 times 4. That's what I'm saying. Get a value of 0. So it's heading towards 0. From the right-hand side, where x is greater than 4, it looks like we're approaching a value of 4. So since from the left we're approaching 0, but from the right we're approaching 4, that just means that the limit as x approaches 4 of f of x does not exist. Since the two sides cannot agree on a single y value to kind of approach and meet up at, it just means that there's not going to be a limit for that particular x value.